Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 9. Students, at this point I will congratulate to you people that we are at the end of the example which we start from lecture number 3, and inshallah we will end this lecture, that example, in lecture number 9. But remember, this is end only for me, not for you people. You people have to do something more. You have to go to DTM method, you have to collect the final movements, and you have to design for that movement. I will show you a little bit procedure, and the rest of the work is of your. Okay, now let me show you here. This is the example which we start, okay, in lecture number 3, and these are the data, and we passed from all these steps, okay, which we basically covered in lecture number 4, lecture number 5, 6, 7 and 8, and in the today last lecture. Clear? So we did all these steps, we did these diagrams, we draw these diagrams, we do these Excel sheets, and in today lecture, basically in lecture number 8, what we basically did, let me recall you some steps of that lecture. Okay, so we start basically pattern loading. Okay, we discuss a little bit okay, about pattern loading. What does it mean? What we have different types of pattern loading. So we run the analysis for this pattern loading. We denote this from by P1. This is my P3, okay, and this is my P5, I think so, and this is P4. Okay, so we run the analysis for these loadings, and today you will see the final results. Clear? So here we have these read values, okay, which we got from P1. And remember, we have to compare P1, P3, P4, P5 against, okay, P2. This value, these values, okay, and these values. Clear? And this is for interior story, and this is for top story. Clear? And this is P3 loading. Okay, you see here, this is P3, which give us the maximum positive movement. And this is for top story, and this is for the interior story, the maximum positive movement, the red one you can see. Similarly, this one for P4, and you see the red values, that is our required value for interior story, and this is for top story. And similarly, we have interior story in case of P5 loading. This is P5 loading, and this is bending moment for basically for P5 loading, that is this red value. Okay, so I summarize all the results. Okay, let me show you here in this distribution table. This distribution table is very important, and I already discussed this distribution table. Okay, the first two tables, the first one is for top story, and this one is for interior story. Clear? You see, we already explained this table, these both tables, okay, in lecture number 5, I think so. Clear? So I don't explain this, I will explain this one. Okay, now you see here, this is P2 loading. Okay, as by the ACI code, remember I already shared this point in lecture number 8. Here in this statement, the final design movements which we should guard from these loading cases. Okay, it should be compared, these load cases should be compared with this loading pattern, that is this loading pattern, which is P2. P2 is a loading case which have a full UDL dead load, okay, which containing full dead load plus full live load. Remember, full live load. Okay, and what does it says? The final design movement shall be not or shall not be less than for the case of full factor dead load and live load on all panels as here. This is ACI criteria or section 13.1.6.4 says. So let me show you this statement. Okay, I summarize all the results right here. This is our P2 loading. P2 loading means that we have full live load. Okay, we apply full live load. We doesn't multiply 3 by 4 with the live load. Clear? And we got these movements at different locations. Okay, you already know these locations. This is my exterior. Okay, in exterior panel, this is my E negative, M positive, I negative. I already explained it in lecture number 6. And these are the slab movements, remember. And these are the beam movements, remember. Because it is multiplied by the factors. Clear? Now, what we have to do, this is E negative. This is the exterior negative moment. We have to compare this E negative with the desired load pattern, and that desired load pattern is this one. Okay, so here we have that is 50. So 50 is less than 56, so that's why we will use this one. Okay, this value, and that is the beam. In the beam we have a negative movement, E negative, exterior negative movement will be 44. Okay, and we have to find the fast movement now for this 44. This should be remembered. Okay, we have to find out the fast movement, and I already find out the fast movement for this 44 in P2 loading. Let me show you. This is very important. This is interior story bending moment right here. This tab shows, and here we have not this one, I think so. This is bending moment for, yes, for P2. This is for top story. Yes, for top story. For top story you see this 44, and the fast movement is 33.67. Okay, so we will design, okay, for this 33.67. now not the final moment, we have to factor it, and we have to add this with dead load moment, remember. But I just to show you that this is our final moment right now, E negative for live load case. Clear? Now one moment is clear, so we will, these red value shows that we will finally choose these values. Okay, now the next one is M positive. So M positive, now you have to compare this with the load pattern there, this one. Clear? And not this one. Okay, this one. Okay, this P3, because here this point will give us the maximum positive moment, and the maximum positive moment you see here, this yellow color, this is 101. So 101 is less than 110, so that's why we will use this moment, that is 75. So 75 is our positive maximum moment in the exterior panel. Remember, it should be note down here. Let me draw these figures. Okay, let me draw here. Okay, so now this is my E negative location. Okay, this is my positive location. This is my I negative. This is my I negative. Okay, this is again positive. This is again I negative. Clear? I negative, positive, and I negative. Okay, this is positive, and this is E negative. Clear? E negative. Now the final movement which I got here is for, remember, for live load only. Okay, only for live load, not for dead load. We have to add the dead load movement with this moment, and for this case we got 44. But remember, we have to find out the fast movement. Okay, now the next one is 75, that is plus moment. Okay, so the next one is here, this is 75, and this one now will be the final, because we do not need here to find out the fast moment. Okay, And the next, this one, we will find this one. Okay, let me draw here. Clear? Now here you see minus 184 and 172. Okay, so we have to compare this with this case P4, this loading pattern. It will give us the maximum, but as you see, we got here minus 146 and 143, so these values are lesser than this one, so that's why we will use these values. This is minus 125 and 117. So here we have, this is 125 minus 125 and 117. We will use 125. Okay, now here we have what value? Let us check it. You see we have 69. Clear? And it is the interior span, this P1 now here. Okay, this is important. Here you see P1 case, it will give us the maximum positive movement in the interior panel, and you see 86. So 86 is more than 69, so this case is now governed, and we drop this value, we ignore this one, and we will choose this one. So this red one will be our negative movement, that is 58. Now where it is, this one, this is 58. Clear? These are our beam movements, remember. Now this case is very important case. Okay, remember this movement may consider, okay, this value as well, this one. Okay, R, if SE code already explained that if you don't know about your pattern loading, your delocation of your live loading, because there is this is all about probability. Remember, live load is all about probability. Okay, for example, as we calculate this negative movement for the live load case, when these two panels are loaded with the live load. Okay, so this kind of movement will be generated. Now if let's say, for example, we don't have this case, and this case may occur here, let's say here. Okay, now here you will see the movement, and now you need to run the analysis for this case and check what amount of movement come here. But what I suggest, basically you need to design for this movement. Okay, go for these values, 125, okay, or 117 are the average of these two. Or either you can design for this minus 96, clear, this value you can design for this. But if I already explained, this is all about probability. If this case occurred, so you need to run the analysis for this case and find the value of negative movement right here, and I think so that value will be this 125 and 117. Okay, so that's why let's say we will use the full factored movement, that is minus 96, or either you can use this minus 125 or 117. Clear? So this is because live load totally depends upon the probability. Okay, if you know about the pattern, let's say for example these are the shop, okay, these are the shops and these are the verandas, so you already know there is greater probability of live load, that the live load will be here, maximum live load will be here, and in the shops there will be lesser amount of live load possibility. Okay, the probability here will be lesser as compared to the veranda. But let's say for example if this is, let's say I will show you in another way, that for example we have let's say this is our shop. Okay, this is our shop, and let's say this is our shop, and this is our veranda. These two panels containing our veranda portion. So here is the live load. Maximum live load probability will be here, and here will be no live load, because in verandas basically the live load pattern is exist. Okay, so that's why then in that case you need to find out this you need to assign this movement right here. Okay, because there is larger negative movement. Clear? So this is all about probability. Okay, and it depends upon the choice of structure engineer. Clear? So let's say we also use 125 or the load or the moment which I basically show here. Clear? So this is the whole summary. Now we go for the design. Now this slide, these are the final slides which give you fruit of your whole calculation. Okay, here you got your fruit. Okay, these slides are very important. It is the summary of the whole 9 lectures, right? Okay, so here we are at the end. We see AB panel, B joint, BC panel, C joint, CD panel or CD beam, D joint, DE beam and E. Clear? And similarly we showed the locations: E negative, M positive, the midpoint, interior point, then again midpoint, then interior point, then okay. So we already know about this. Now the dead load movements, these are the dead load movements, remember, and the fast movements, remember. These are the dead load fast movements. I already picked these values from those tables. Now these are the live load, okay, fast movements. Remember, let me show you this value. This is minus 28.22, and you already see here that for exterior, okay, this is 44, I think so, and this 44, this is basically for the P2 loading. Clear? So let us check P2 loading for interior for top story. Okay, and yes, this is for top story. Remember, we just only explained this is for top story. You have to, the same calculation will be done for the interior story as well. Okay, for interior story as well. Remember, you have to compare these results with these values. Okay, and here for this one, this is 55 and this is 58. Clear? So from where we got this value, that is 28, I think so. So here we have 19 point this value. This is critical. These are the fast movements. This is for interior story and this is for exterior, for top story. Now I am interested to find out that value, okay, which is this one, this moment, live load maximum movement cap feet. This is negative value. Okay, so you see here that for top story, remember, this calculation is for top story. So for top story, E negative is this one, it is minus 28.22. But remember, as you see here in this distribution table, that we got it is 44, because P2 case is the governing case, not this one. Okay, this 40 is less than the 44, so that why we just dropping that value and we will choose this one. Now we need to find out we have to bring that value fast moment. We just enter equal and go to P2 loading case, that is for top story here, and here we have, this is 44, you see, this is 44, not this one, but we have to consider this one. Clear? This is the fast movement because we have to design for the fast movement. And yes, go. So here we have 33.67. Clear? 33.67. Now let us check it, okay, whether it is right or wrong. Clear? So this one, clear, and yes, this one, because it is already multiplied with the factors, and this is the fast movement. Clear? Now the next one is what? The next one value will be here. You see this one. Okay, the next one is M positive. So M positive will be, let's say we check it that in this case P2 case is the governing case. Okay, you see here this one 75. So let me bring that value. This is equal, okay, and go to again P2 loading case, that is this one for top story. Clear? And here this one 75. So 75 will remain constant. Okay, so just bring that value. Okay, 74 or 75. Now I negative. So in I negative, if we check the distribution table here for I negative, P2 case is the governing case. So minus 126 will be right now we need. So equals, and go to P2 loading case for top story. Remember, this is for top story right here, bending moment for top story P2, and here we have minus 125. So here we have critical moment minus 124, this one. So here we have similarly this one equals and M positive. So for M positive, let me check the distribution table. So for M positive, you see the governing case is this one, this red value. Okay, that is P1 case. Now we go to P1 case, okay, where we are this one equal, and go to P1. So you see here this is for interior story, for top story this one, this value 58, and 58 will be the design moment. Okay, this one, this value. Okay, and the rest of the value you see here I negative, this brown color. Okay, it shows that here you are allowed, either you are taking this one or either you are taking the value which you got in P2. Okay, so these are the values and these are the repetitions of these values. Okay, so we don't need these values. Okay, now you see this is the final step. You see we add dead load and live load. Okay, so you see I multiply 1.2 with this factor moment which I got from the dead load analysis, and 1.6 with this live load. Okay, with the live load, and I got basically the sum, that is 76.66, and the net moment will be this one, these one. Okay, let me no. Okay, now you see this value is basically this is moment. This is in kef feet. I convert it into kef inches. Clear? This is very, very important. Now into kef inches it is around about 1000. We have to now design for these final moments. We need to find out, remember this is our beam, only we are analyzing beam in the east-west direction, that is 25 feet span. Now you see the width of the beam is 14 inches, the total depth of the beam is 20 inches, the effective depth I'm using 2.5 inch cover. Okay, so that's why the effective depth is 17.5 inch. The strength of the concrete, that is FC prime 3 kSi. the fy is 60 psi, and my area, here is my area. I just plug the formula of area, okay, and I got the value is 1.024 inch square. Now my minimum, okay, my minimum steel area is this value, that is 0.80, and my maximum, okay, I using the maximum steel ratio is 0.0136. You must know about how to calculate row minimum, okay, you already know it, how to calculate row minimum and how to calculate row max. Okay, so you must know it, this stage you must know. And once you calculate these values, what we have to check, you have to check your ductility, whether your A is greater than A is minimum, okay, and whether it is less than A is max. So you see, this is my AS max, okay, and this is my AS minimum, and this is my AS provided. So you see, AS provided is greater than AS minimum but less than this one, so my answer is okay. If it is not, this condition is not fulfilled, so here you will see not okay. So this means you have to repeat your procedure. Okay, now for this, if let's say I'm using number 6 bar, so here you see I'm using the area of steel, that is number 6, I got 2 bars. So for negative movement, which I showed here, okay, here let's say I draw the cross section, okay, here let's say I draw the cross section right here. Now let's say this is my beam, okay, let me draw the section, okay, this one. Now you see here is one column, then the next column, then the next column, and in the next column, and so on. Clear? So in top region I have to provide 2 bars, okay, in the top region I have to provide number 6, okay, 2 bars. Now the next one is this one, in positive, okay, so my positive movement is 2091.0811. so in that case the whole data is now the same. The only thing is that for positive movement you have to check whether you have need a rectangular beam analysis or whether you have need to run your T-beam analysis. So this is my HF and this is my clear span, okay, and here I have the effective width of the T-beam, I calculated it, okay, and the net value B effective is 71.49. okay, I calculated my A value, that is the small a, as my small a is less than HF, so that shows that we need to run the T-beam analysis. Clear? If this value is more than this one, so we need to run the rectangular beam analysis. Clear? Now here the formula is a little bit different, because in this formula now we are using this width, okay, not that 14-inch width, because in T-beam you must know about the procedure how to design a T-beam, okay. And I already uploaded recently, I already uploaded this lecture. Let me show you here from McGregor book, okay, this example, and I thoroughly explain in 3 to 4 lectures how to design a T-beam and how to basically I pick all these values, okay, and the tables, and I insert these values in my Excel sheet, okay, and here you see the small a. Clear? If this small a is lesser than your HF, so you need to run your T-beam analysis. Clear? And here I think so it is explained here, okay. So you see a is less than HF, so that's why you need to run the T-beam analysis. Okay, so I already explained this, and I will share the link of these lectures in the description, so please watch those videos to understand how to design a T-beam. And on my channel there are so many examples available how to design a T-beam, how to design a rectangular beam, both for flexure and both for shear. Clear? So I got the moment, the steel area is 2.261, and for this, if I'm using number 6 bar, so I have to provide 5 bars. So for positive movement, I need to provide here in this span. Okay, this is my AB span. Okay, this is my AB span, and this is C, and this is D, and this is the last span, that is E. Clear? So for positive movement, I need 5, okay, number 6 bar here, 5 number 6 bar. Clear? Now at the B point, as I have a negative movement, so for that negative movement, you see the negative movement is 3078. Now this is interesting, this is very interesting. Okay, you see 256.50. okay, and for this I need 9 number 6 bar. Clear? So here I have to provide for, okay, 9 number 6 bar. Clear? And similarly I will provide the same reinforcement at this. Okay, although there is a negative movement will be smaller as compared to this one. So here you are free, either you are using this reinforcement, or you are decreasing your movement. Let me check it, which value I'm using. This is same value. Okay, you can decrease it by just picking the value from P2 loading case, and I think so that is around about 141. okay, if it is converted to fast movement, so this is around about 96.99. okay, 96.99. so it will decrease your demand. okay, and for that you see you have add bars. Now for your M positive you need 4 bars. Clear? And similarly you need to run similarly here this one. Okay, this one. So here I have 1530, and you need to check whether you need to T-beam analysis. So we see okay, so this suggests that you need to run the T-beam analysis, and you need 4 number 6 bar. So here in this PC panel you have to provide 4 number 6 bar. Clear? And here let's say this is at number 6 bar. Okay, and again here you have to provide this one, and here again you need to provide that reinforcement 5 number 6 bar. And similarly here you have to provide the same reinforcement, this one, and here you have to provide that reinforcement 2 number 6 bar. Okay, this winds up the flexure design of your B. Okay, in the east-west direction. Okay, for interior frame. Now you need to design for the shear reinforcement. We have already know the shear values, we calculated it, and that's winds up your design of your B. But still you have to design for the slabs, and for the slabs movement you have to go to my YouTube channel, and you have to watch the DDM method. Total 15 to 16 lectures available and thoroughly explain. Let me discuss a little bit about that, how to design. Remember, let's say in this diagram you see here we have this panel, we designed this beam Okay, for flexure you have to, you people have to design for that beam for shear reinforcement. Okay, that is simple. And that is the next thing is this is the slab designing. Now how to design the slab? Okay, we already know that we calculated the values for the slab. Okay, so we have to divide this panel into, okay, we have to design this panel into column strip. Okay, right in this way. Okay, and middle strip. This is half middle strip and this is half middle strip. Now here you see from your analysis that you have this is E negative. Okay, so you need to find the moment due to dead load and you need to find the value due to live load. Okay, so here you see, let me share that value. Okay, this one. Okay, remember we just do the procedure for top story. Again again you need to repeat the same procedure for your interior story. And for interior story you see the reinforcement right here. Okay, and one thing more, let me check it. Okay, because I see this value is 256, and here I have an example in this diagram. You see here, not this one, yes, this one, you see 256. So they are using for 256 they are using 2.68, but here they have the cross section of the beam is, you see, 24 inches, and we have, and 12 inches, we have 14 inch and we have 20 inches, but you see the reinforcement is close. The reinforcement is close. We are using 4.041. Why this reinforcement is larger than that one? Because if you are increasing the depth of the beam, your area of reinforcement will be decreased. If you are decreasing your movement, your depth of the beam, it will increasing your, okay, your steel area. So let's say if I check this one is 12 and this one is 24. Clear? So you see the steel area is changed now. Okay, it is decreased from that value, and this value is fixed 21.5, and they are using FC prime is 4 KSI. Okay, so you see 2.948. This is the beauty of this calculation. All things are dynamically changed. Okay, now for 256, 12 inch width of the beam, having 24 inch total depth. Okay, and yes, having effective depth is this much and FC prime is this much, you will now 2.94 and they have 2.68. so this is close. Let me check some other values. Let me check it. Here we have minus 274 and 159. So 159, I think so, 174, okay, and 127. Okay, so 174 is a little bit close to 156. For this we are using 2.26, and for 159 they are using 1.67 because they have a larger depth. Okay, they have a larger depth, so that's why there is a little with smaller amount of steel reinforcement. So this is the way how to compare. Okay, and they have a length of roundabout, let me check the length of this beam. They have around about a length of 30 feet. Okay, round about 33 to 30 feet length. Clear? So this shows that our design is a realistic design. The next thing is that you have to check these movements with your approximate movement coefficient, that is 1 over 11 and 1 over 19, 1 over 14, 1 over 16, 1 over 9 or 1 over 10. Okay, and check the results whether these results are close or not close. Clear? Now discussing here the movements. Now here you need to find the movements, okay, mu. Now the movements is 1.2 due to dead load movement plus, okay, this will be md now, okay, because we got the movements, and 1.6 due to ml. Now you see md is already known, here, okay. Let me show you that value, clear, md. Yes, this one 5, okay, this 5, remember, this 5 is for E negative, so 1.2 times 5 plus 1.6 times the final value which we got here in this moment distribution table, and you see that value is 8, okay, 8. So 1.6 times of 8, you got the value right here, okay, this value E negative. So you got the value for this middle strip, and the value of mu which you got, okay, let's say that is 20, okay, kef feet, I think so, that will be the total moment, and you have to divide that moment by the width of this middle strip. You got 4 feet, and then the value which you got, you have to find out your area of steel. So I thoroughly explained this procedure in my those DDM methods, okay, DDM method, and those methods are available in my YouTube channel, so please go and watch, okay. And remember, in the half metal strip, as you see, we have 2.833 here due to dead load. We have to find for this 4, so 4 due to live load, and 2 point, I think so, 2 point this one 1.87, okay, 1.87, and 1.87 times 1.2 and 4 times 1.6, you got the middle strip movement, okay, here. And then you run the analysis for that exterior frame, and that exterior frame will also be divided into column strip and middle strip. So from that analysis you will got the movement for the middle strip, add these two values and divide that by the width of the column strip, okay. So from that you find out the movements for slab design, and you finally design the slab for those movements. So it will just only to give you an idea how to collect all the movements, okay. And the rest of the procedure is explained in those videos in the DDM method, okay. So go to my YouTube channel and watch those lectures. This winds up this example, okay. If you people have any questions, okay, any confusions, any other vague statements, you can ask the questions. And next, inshallah, that will be lecture number 10. I will explain another example, and that will be from McGregor book, that is example number 13.7, and I will cover that example in one video. So my key purpose of this total detail of 9 lectures, that I will thoroughly explain each and every concept of the equivalent frame method, because this is the method, is so complicated method, and it has some complex concepts, and this method is not available on YouTube, okay. So that's why I explained it thoroughly. Thank you for watching. See you in next lecture.